So today we will be discussing TIFR 2020 problem question number 4. So this question, it is stated like this. If you look at the question, then let n be a strictly increasing bounded sequence of real numbers. So that limit n tends to infinity n is a, and the function f is defined from a1 comma a to r, and it is defined to be a continuous function such that for each positive integer I, the restricted to each of these small intervals, closed and bounded intervals, it is either strictly increasing or strictly decreasing. So consider the set, and we need to figure out the cardinality of B. Okay, so the cardinality of the set B. Let's get on to understanding the cardinality of the set B. So this is one of those classical TIFR problems. Now, if you look at this question, the first thing that should attract, the first thing that you should be attracted to is that this is a strictly increasing bounded sequence and its limit is n. Second thing is that the function at each of these intervals are either strictly increasing or decreasing. So what does that actually mean? It means that since f is given to be a continuous function, so since f is continuous and f restricted to ai comma ai plus 1 is either strictly increasing or strictly decreasing. Okay, so since f is continuous and this is either strictly increasing or strictly decreasing, what it means is that this actually implies that in each of these ai comma ai plus 1, f is injected. Okay, so see, if you have a strictly monotone continuous function, then it is bound to be injected. The proof you can actually do it like this, that what is one of the ways we can prove that a function is injective? It is f of x1 not equals to f of x2 implies x1 not equals to x2. So this is one of the ways you can actually prove injectivity of a function, because the forward directional definition goes like this: x to x2 implies f of x1 equals to f of x2. Okay, so if I just take this statement, this is equivalent to that. Now since our f is strictly decreasing or increasing in these closed and bounded interval, what does that mean? So if f of x1 is not equal to f of x2, this precisely means, suppose it is strictly increasing, then f of x1 greater than f of x2 will imply that x1 is greater than x2. Thus, not being equal here implies not being equal here. Okay, so it's as simple as that. Similarly for decreasing as well. So strictly increasing, or for strictly monotone functions, this is the first point in this problem that you might want to use. So this is, let's say, remark 1. So strictly monotone continuous functions are injective. Okay, so the moment you have injectivity here, what we can move forward to are two things. So see, since E in tends to E, that means what? In real line, if you put down EIs, how are they given? A1, A2, and in an increasing manner. Okay? So as you can see that in the question, it is a strictly increasing bounded sequence. Hence, A1 is less than A2, then A, and it goes on like this. Okay. So that means what? That if you take this, if you take the interval given in the problem at E1 comma A, so this interval actually contains all these smaller intervals as well. Because since it is strictly increasing function, there is some limit here somewhere. So if you take A1, A2, then A2, A3, all these things falls right under it. Okay. So the fact is that since it is given that if restricted to AI comma AI plus 1 is either strictly increasing, so I will write strictly increasing or strictly decreasing. What does that actually mean? It means that I can very well take my entire function f to be completely, I can actually take it to be strictly increasing from E1 comma E to R. So this is also a possibility. If the function is entirely strictly increasing from A1 comma A to R, then in these intervals it will have to be strictly increasing as well because it is entirely increasing. Now if you look at the coordinate that we have to find, it's like the collection of all such m such that there exists infinitely many x such that f of x equals to m, right? But now if I have this, so now if I have this, that if f is strictly increasing, so now I'm not taking any restriction of f, I'm actually taking it is strictly increasing everywhere. All right. So the moment you take it, that means what? It makes sure that f becomes injective. All right. So the moment f becomes injective, the cardinality of this set becomes 0. You see that? Because see, if f itself is injective, then there, uh, the set which has points like these in R, such that there are infinitely many x which makes f of x equals to n, there is set kind of. Okay, so hence the cardinality. There are no such points because if f is injective, then there cannot be infinitely many x such that f of x is a single number. The injectivity prevents that from happening. Okay, so thus one possibility is the cardinality is 0. So this is one possibility. If I take f to be entirely strictly increasing. Okay, but let's say if it is not, let's say that the cardinality, the function is not entirely strictly increasing. Okay. So then what happens? So since now I am using the fact that if restricted to ai comma ai plus 1 is strictly monotone. So I mean, strictly monotone means it is either increasing or decreasing. So which is a given hypothesis. Now, if you look at it, let's say this is A1, A2, A3, and it goes on like this as an increasing sequence. So if I have, there are, and another given hypothesis, there are infinitely many x in this interval A1 comma A, as you can see in A1 comma A, A1 comma A, such that f of x is equals to n, then all these x has to lie in different intervals. Okay, so let me say that again. So it's kind of like this, that say, let's say x1, some x1 is here, then another x2 for which f of x2 is equals to n cannot lie in the same interval. X2 cannot lie here in the same interval A1 comma A2. The reason being, f is injective in these intervals. So since in these intervals your function is always injective, what happens is that there can be at max one x from each interval where f of x is equals to n. Okay, so now infinitely many, we can actually take a countable collection of them. So now we have this, the sequence n, this converges to A, right? Hence, if I define two subsequences, A1, A3, A5, A7, and it goes on like this. This is, let's say, one subsequence, and another subsequence like A2, A4, A6 goes on like this. Both of these subsequences will independently converge to A, since it is a convergent sequence. The n is a convergent sequence, correct? Now, since I'm picking these xi's from each of these intervals like this, I can very much well write something like this. See, x1 is between A1 and A3. So then it is pretty much in between A1 and A2. So then it is pretty much in between A1 and A3. Correct? So we can write for the points, for the points or for the xi's for which f of xi is equals to n, we can actually make them bounded by these two convergent subsequences elements. So what we are actually doing, we are doing something like this. X1 is from A1 to A3. X2 is from so uh, so let's say it's like this. So A1 to A2. X3 is from A1 to yeah. So X2 is from A2 to A3. X3 is from A3 to A4. It goes on like this. Okay. So what happens precisely? So we have a subsequence like this here, and I have subsequence like this. So in both the terms up until this point, right? So if I take the sequence, let's say xk, then this sequence is kind of dominated by two subsequences. So let's say for some a and k and plus 1. Okay, so I can always find these two subsequences. So you can, whatever we have said, that you can actually apply it here as well. So then A1 to A3, A2 to A4, you can take these like this. So in that way, if you take it, then this will become like this. And this is A1 to A3, then this is what? Then this is your A2 to A4, this is your E1, 3 to 4. So this will be from A3 to A5, right? So this way you can also construct the uh, this way you can also construct two subsequences. So now since this sequence is bounded by these two subsequences, by squeeze theorem, both of these tends to A. Hence, so limit nk tends to infinity, and similarly nk plus 1 tends to infinity. Both of these two sequence tends to A. So what happens is that this will tend to A. Okay, but now what I have is this. What I have now is for each of the xk's, f of xk is practically equals to m. That is how we chose those xi's. Remember that these infinitely many xi's, these are practically these xi's. All right. So for each of a key, f of xk is equals to m. Right. Now, since f is continuous, if I have the sequence xk tends to a, then I will have f of xk tending to f of t because of the continuity property, right? So what does that mean? It means that basically the so this is for each key, all right? So what does that practically means? It means that the only element that is present at the set is only a, because f of a is precisely m. Why? Each of this f of xk is m. So if you take the sequence, then this sequence is nothing but m, m, it goes on like this. And if this sequence converges to f of a, this is a constant sequence, then f of a has to be equals to m. All right. So hence the answer to this question is the cardinality of the set B is at most 1. So we have proved that it can be 0 if f is completely and strictly monotone everywhere. If not, then we have the only possibility where f of x is m is a. So this problem actually uses two main ingredients. The first thing is strictly monotone implies injectivity. Secondly, uh, secondly is this, that any subsequence of a convergent sequence converges to the limit. These are the main two ingredients to solve this problem. Okay, so this is it for today. We will meet next time with another question from TIFR 2020. Fine, thank you for joining us. We will meet next time.